In this video, we will discuss Gauss law. Gauss law states that for any distribution of charges, the total electric flux linked with a closed surface is 1 by epsilon 0 times the total charge present within the surface. So it means if we will take a closed 3D surface and place amount of charge Q inside the closed surface, then the total electric flux of the closed surface will be phi is equal to the total amount of charge present inside the closed surface Q enclosed by epsilon 0. So according to Gauss law, phi is equal to Q enclosed by epsilon 0. But we know that according to flux definition, phi is equal to closed surface integral of, because we are taking a 3D closed surface, so closed surface integral of E dot dA. So therefore closed surface integral of E dot dA is equal to Q enclosed by epsilon 0. So this is called Gauss equation, or mathematically we can represent Gauss law by this equation. So how we get that closed surface integral of E dot dA is equal to Q enclosed by epsilon 0. Let's see how we'll get closed surface integral of E dot dA is equal to Q enclosed by epsilon 0. So let's take a sphere as our 3D closed surface. At the center, place amount of charge Q. At the center of the sphere, place a amount of charge Q. So what will be the flux of the sphere? So as per flux definition, closed surface integral of E dot dA, flux is equal to closed surface integral of E dot dA. So dA is here the small elements are the small area. So because the charge Q is present at the center of the sphere, so at every small area, at every dA, the electric field will be constant, because the distance between the surface and the center is the radius r, and the direction of the electric field will be normal to the small area, and the direction of the surface, small area surface direction will be same the direction of the electric field. So here theta will be 0 degree, and at every small area theta will be 0 degree. So in every small area electric field is constant and theta is 0 degree. So you can write integral of E dA cos 0. So E is constant, so I can take out of the integration. So E integral dA, because cos 0 is 1. So phi is equal to E integral of dA. So integral of dA is what? The total surface area of the sphere. So the total surface area of the sphere will be 4 pi r squared. So E into 4 pi r squared. So E is what? E is equal to kq by r squared. So in place of E, we can place kq by r squared. So k q by r squared into 4 pi r squared. So r squared cancelled. Our k is equal to 1 by 4 pi epsilon 0. So instead of k we can write 1 by 4 pi epsilon 0. So 1 by 4 pi epsilon 0 into 4 pi. So 4 pi got cancelled. So here 1 into q. So what's remain? Q divided by epsilon 0, because we are taking a closed 3D surface. So the q has to be placed inside the closed surface. Then here q enclosed by epsilon 0. So we can derive the Gauss law from here, or we can simply write closed surface integral of E dot dA is equal to q enclosed by epsilon 0. So this is the mathematical representation of Gauss law, and we can prove Gauss law by this. And Gauss law is mainly used to find electric field by using this equation, or we can find any 3D surfaces flux by using flux is phi is equal to q enclosed by epsilon 0. Not only the sphere, any kind of 3D closed surface. If we'll take this type of a 3D closed surface and take a charge, amount of charge q, then the flux will be q enclosed by epsilon 0. If we will go this way also, we will get q enclosed by epsilon 0. We can use this formula to find electric field, but we know that E is equal to kq by r squared. Then what is the necessity of this equation to find electric field? So if there are countable number of charges, then we can use this formula to find electric field. But if there are uncountable number of charges, we can use this formula, but it will be very complex to find electric field. We have to do a lot of lines of force, or have to find a lot of electric field, then we have to add them. But using this equation we can easily find the electric field. But Gauss law has some limitations. We can't use Gauss law at everywhere. There are some points we have to remember before using Gauss law. There have to uncountable number of charges and uniformly distributed. Then we can use this equation to find electric field. If there are countable number of charges, we can't use this equation. And Gauss law is used only in 3 situations. The first one is if uncountable number of charges are uniformly distributed in a wire, then we can use this equation or Gauss law to find electric field. And this is called line of charge or wire of charge. So this is the first situation where we can use Gauss law to find electric field. And the second situation is if the uncountable number of charges are present in a sheet and uniformly distributed, then we can use Gauss law to find electric field. And this situation is called sheet of charge. And the third situation is if uncountable number of charges are present in a surface of a sphere and has to be placed in a uniformly distributed manner. There we can use Gauss law to find electric field, and this situation is called sphere of charge. So in these three situations we can use Gauss law to find electric field. So let's see the first situation, line of charge. Let's see the first case, line of charge. In line of charge we have to use this equation to find electric field. So before using this equation we have to take a 3D closed surface, because Gauss law is only valid for 3D closed surface. So I have to take an imaginary 3D closed surface which is called Gaussian surface. So before taking an imaginary Gaussian surface we have to consider two things. The first thing is, in every surface of the Gaussian surface the electric field has to be constant, and the theta also has to be constant in every surface of the Gaussian surface. So theta is the angle between the direction of electric field and the direction of the area of the surface. So I have to consider these two things has to be constant. So I have to choose a 3D closed surface where in every surface of the 3D closed surface the electric field and the theta has to be constant. Then after we can take the electric field out of the integration, then we can easily find the electric field. So I have to take an imaginary Gaussian surface where the electric field and theta has to be constant. So for line of charge, what is the lines of force direction will be? So if we will place the uncountable number of charges in this wire, then the lines of force will come out like this. It will come radially everywhere. So because there are uncountable number of charges, so lines of force will not come out like this. So if we will take a cylinder as our Gaussian surface, and we will place the line of charge at the center of the cylinder, then what will happen? So lines of force will come like this, and because the line of charge is present at the center of the cylinder, so the distance between the line of charge and the curved surface. So if we will take a very small areas dA of the curved surface of the cylinder, then the distance between every dA and the line of charge will be the radius of the cylinder. So electric field will be constant at the curved area, and the two flat areas, in the two flat areas the lines of force direction will be like this, and the flat surface direction will be normal to the surface. The area's direction is normal to the surface, so area's direction will be like this, and the lines of force direction like this. So the angle between them is 90 degree. So theta is 90 degree. So cos theta will be cos 90 is equal to 0. So the flux will be in the flat surface will be 0. So here electric field is constant in this flat area also. Here also the same. So here electric field is constant and theta also constant in the flat area. In the curved area, theta will be constant because in the small areas the lines of force will pass normally through the surface, and the area's direction will also the normally through the surface. So theta will be 0 degree in the every small area of the curved surface. So you can see in every surface the electric field and theta is constant. So we can choose cylinder as our Gaussian surface for line of charge, but we have to take the cylinder like this only. If we'll take the cylinder like this, then what happen? The flat surface will face the lines of force like this. So when the lines of force will touch at the center of the flat surface, then the distance will be short, but when it will touch at the ends, the distance will be more and the angle will be changed. So here now not electric field is constant, neither theta is constant, so you can't choose cylinder as our Gaussian surface like this. So you have to take cylinder as our Gaussian surface for line of charge like this only. If we'll take a cuboid as our Gaussian surface, then what will happen? So if we'll take a cuboid as our Gaussian surface, the lines of force will be touch the flat surface like this. So here neither electric field will be constant nor theta will be constant. So I can't choose cuboid as also our Gaussian surface. If we'll choose a sphere as our Gaussian surface, then what will happen? Then the distance at the end of the sides will be less. At the center the distance will be more. So electric field is not constant, or neither theta is constant. So we can't choose sphere as also our Gaussian surface. So only we can choose as a cylinder as our Gaussian surface for line of charge, and we have to take this. So in a cylinder there are 3 surfaces to become a closed surface. In the first, if we'll take it as our first surface, then here electric field is constant and theta is constant, and theta is 90 degree. And if we'll take the flat surface as our second surface, then here electric field is constant and theta is 90 degree. And in the curved surface, if we'll take the curved surface as our surface 3, then the electric field is constant and theta is 0 degree at every small area of the curved surface. Then what will be the closed surface integral? If we'll remove the closed surface integral, it will be integral of E dot E d E1 d A1 cos 90, because in first surface the electric field is constant and in every small area the theta is 90 degree. So plus integral of E2 dA 2 cos 90 plus integral of E3 dA3 cos 0 degree is equal to q enclosed by epsilon 0. So cos 90 is 0. So the total term will be 0. Here also cos 90 is 0. This total term will be 0. So what will remain? Integral of E3 dA3 cos 0. Cos 0 is 1 and E3 is constant at every small area of the curved surface. So you can bring the electric field out of the integration. So E integral of dA3 is equal to q enclosed by epsilon 0. So integral of dA3 will be what? The total surface area of the curved surface of the cylinder. So what is the formula of surface area of a curved surface? Is 2 pi r. 2 pi r L, where r is the radius of the cylinder and L is the length of the or height of the cylinder. So instead of integral of dA3 we can write E into 2 pi RL is equal to q enclosed by epsilon 0. So what will be E? E is equal to q enclosed by 2 pi r L epsilon 0. So q by L is lambda. Lambda means linear charge density. So linear charge density means per amount of charge present per unit length. So in 10 centimeter length, if there are 5 coulomb of charge, then lambda will be 5 by 10 will be 1 by 2 coulomb per centimeter or meter. So this is linear charge density. So instead of q by L we can write E is equal to lambda by 2 pi r epsilon 0. So this is the formula to find electric field of a line of charge. So here we can see the number of charges doesn't matter to the electric field. The thing is matter is the amount of charge is placed in per unit length and the distance between the line of charge and the point where we find electric field, and the permittivity of the medium. So we can take a small cylinder as compared to the length of the wire, because at the ends the lines of force will be change the direction. So we have to take small cylinder as compared to the length of the line of charge, and where we have to find electric field that should be at the middle of the Gaussian surface. So E is equal to lambda by 2 pi r epsilon 0.